Hello students, welcome to day 32 of PU2 Brahmastra series. So today we are going to do the last chapter of the chemistry, that is chemical kinetics, and I can assure you if you watch this one video and do all the questions, then definitely you will be able to crack all the questions from this particular chapter. Okay, so now let's get started and understand about the weightage and all of this chapter. So this chapter is very high weightage. You can expect 12 marks from this particular chapter, right? And I will say this is one of the very easy and scoring chapter as well. Okay, so there will be one VSA question according to the blueprint, one 2-marker questions, and you will get 3 3-marker questions. And in this 3 3-marker questions, there will be 2 numerical problems and 1 theory question. Okay, clear? Now coming to in this particular lecture, what you will be getting from me. So you will be getting 10 MCQs, HOTS type, 12 2-marker questions, 15 3-marker questions and 15 numerical problems. So if you see almost like 15 plus 15, 30, 40, 52, right? So 50 plus questions we are going to solve in this 1 to 1.5 hours, and if you are able to solve all these questions, then do not worry, you can chill and relax and you can put a tick mark on your chemical kinetics chapter. Okay, so students, now if you are liking these sessions, if this Brahmastra series is really helpful, so please put down your comments, put down your feedback in the comment section. That really motivates us to work harder, right? So just think, suppose you are putting some efforts for some students and or for your friends, and if they do not even appreciate you or they do not give you feedback, right, you will feel that your efforts are worthless, right? So that may happen to even us, even though we are doing our 100%, but still we also need some time motivation, and you are our source of motivation, right? So students, if you really find this series helpful, if you are able to solve these questions, if you are able to find this series helpful in your preparation, then please let me know, and I will be waiting to see your comments. Okay, fine, let's get started now. Okay, one more thing, you all will be knowing already about this. I have been telling about all the videos. There is something very important here, that is PU2 success blueprint test series. Okay, so this test series is specifically designed to help you to get 95% and above in your PU board examination, right? So now you will be getting 12 mock tests here, and which will including 4 part tests and 8 full length papers, and the subjects included will be PCMB. Okay, and you will be getting the questions according to the latest pattern and syllabus. Apart from this, you will also be getting the detailed video solutions, PDF of the solutions, doubt clarification classes, and 1 short revision videos of the chapters, right? So after that, these all things you can avail at a very discounted price of 599 rupees only. So students, if you really want to ace this preparation, then go to the description section, click on the link. You will find a link regarding the test series. Click on the link, go to the page, buy the test series, and get ready to ace your preparation. Okay, fine. Now let us do the questions. Question number 1. 2N2O5 gives 4NO2, okay, plus here it is O2, okay, sorry, 4O2. For the above reaction, which of the following is not correct? Okay, which of the following is not correct above rates of reaction? Okay, so if you know how to write the rate of the reaction, it is very simple. Rate is equal to, rate is equal to minus 1 by 2 dN2O5 by dt, okay, equal to 1 by 4 dNO2 by dt equal to dO2 by dt. Okay, clear? So now question, let us see one by one all the options. So the first option is minus dN2O5 by dt is equal to 2 times of dO2 by dt. Yes. Now if you see, if I equate these two part, right, then what I can write, minus dN2O5 by dt, okay, will be equal to 2 times of dO2 by dt. Okay, Now coming to the next one, minus dN2. So this is a correct relation, right? This is a correct relation. Next, coming to minus 2dN2O5 and 2dNO2D5. Okay, N2O5 and NO2. So N2O5 and NO2, if you see, the relation is like this: minus 1 by 2 of dN2O5 by dt, okay, is equal to 1 by 4 of dNO2 by dt, right? So if I multiply this 4 here, okay, if I multiply this 4 here, then I'll get minus 2 d by dt N2O5, right, is equal to plus dNO2 by dt, right? But here what we are getting 2, and here also there is a 2, right? So this is not the correct answer. Let us see the next one. You have this dNO2, right? dNO2 by dt is 4 times of dO2 by dt. Yes, that you can see. If you multiply this 4 here, you will get this relation. That is also correct. Next one is you have minus 2 dN2O5 by dt, okay, is equal to 4 dNO2 by dt, okay, is equal to dO2 by dt. Okay, I think this option here, this 2 is not there, okay, I remember this is also correct if you write. This one is incorrect because you can see here this is in denominator, here they have given in numerator. So the correct answer for this question will be option number D, okay. Next, question number 2. Consider the following statement in respect of zero order reaction, okay. The rate of the reaction is independent of the reactant concentration. Yes, if you see that rate is proportional to K into A to the power of 0, right? So rate is equal to K, I can write, right? The rate of the reaction is independent of the temperature. No, the rate of the reaction, okay, yes, now the rate only depends on the rate constant, okay, it is not dependent on the temperature also. Next, let us see the statement: rate law expression and unit of K. Unit of K is second inverse. No, second inverse, this one, that is the unit of first order reaction. So this is incorrect. The rate constant of a reaction is independent of the reactant concentration, okay. Choose the correct statement, okay. The rate constant of the reaction is independent, okay, the question is saying the rate constant, okay, of the reaction is independent of the reactant concentration. Yes, that is also correct. See, the rate constant is not depending on the reactant, right? The rate constant of a reaction, the K value, okay, is independent of the reactant concentration. For zeroth order reaction, whatever is the reactant concentration doesn't matter, it is always rate is equal to K. The question is saying that the K value is independent of the A naught value, right? That is, this statement is correct. Now next second statement, if you see, the rate of the reaction is independent of the temperature. No, see, rate depends on K value and K depends on temperature, right? So rate is also dependent on temperature, it is not independent of temperature. This is also not correct. So 1 and 4 are the correct answer. Option number D will be the correct answer here, okay. Next, for a first order reaction, the time required for 99.9% of the reaction to take place is nearly, okay. So this we will derive it, but you should know T 99.9% is equal to 10 times of T 50%, okay. This will be deriving 10 times the time required for the half of the reaction, 100 times that required for the 2/3 of the reaction, 10 times that required for 1/4 of the reaction, and 20 times required for the half of the reaction. So this is 10 times that required for the half of the reaction, okay. Next, when initial concentration of the reactant is doubled, the half-life of a zero order reaction is. So for that you should know the zeroth order reaction formula, right? So for zeroth order, T half, for zeroth order, okay, T half is equal to 0.693, sorry, for zeroth order it is, A naught, okay, by 2K, right? This is the value of T half. Now when initial concentration is doubled, so if it becomes 2 times of A naught, the half-life period of a zero order reaction. So I can write like this, 2 times of A naught by 2K, right? Right, so you can say it is 2 times of T half, right? So the new T half will be 2 times of the initial T half. So the T half increases by 2 times, right? So it is halved, doubled, tripled, remains unchanged. It is doubled. Option number B is the correct answer here. Next, for the chemical reaction, the correct option is, okay, so again we can write down here, it will be minus dN2 by dt, okay, is equal to 1 by 3 minus dH2 by dt, then plus dNH3 by dt, okay, 1 by 2. Clear? So now we can see here a relation between H2 and NH3, right? So what I can say, 3H2 and 2NH3, no, that is not the relation, this is not the correct relation. Minus 1 by 3 dH2 by dt is equal to 1 by 2 dNH3 by dt, yes, this is direct correct relation. Next you can see minus dH2 by dt is equal to 2 times of dNH3, no, we need this 3, so this is also incorrect. Minus H2 by dt is equal to 1 by 2 of, no, again this 3 is missing, this is also incorrect, okay. Next, in collision theory of chemical reaction, ZAB represents, okay, ZAB represents the fraction of molecule with the energies equal to AB, the fraction of molecules with energies greater than EA, the collision frequency of reactants A and B, right? ZAB represents the collision frequency, okay. Next, question number 7, for a reaction, the enthalpy of the reaction is minus 4.2 kilojoule. So if the enthalpy of reaction is negative, that means it is an exothermic reaction. Exothermic reaction means product energy will be less than the reactant energy, right? So here you can see reactant product energy is more, here also product energy is more, here the product energy is less, and here we cannot see. So by just reading the first line, I can eliminate these two options, okay. The enthalpy of activation is 9.6 kilojoule per mole, okay. The correct potential energy diagram for the reaction is in the option. So I can say, because you can see energy of the product is more here, energy of the product is more here, these are endothermic reactions. So but exothermic reaction enthalpy is negative, so we can eliminate these two options. Now here you can see it is almost same, right? So that means this also option is not probable, but here you can see this option looks much more preferable, because here product energy we can see definitely here this difference is minus 4.2, okay, and the energy or the activation energy is around 9.6, right? The correct answer will be your option number B, okay. Next, the given graph is a representation of kinetics of the reaction, okay. The y and the x axis for 0 and first order reactions respectively are, okay. So for 0th order reaction, okay, the given graph is a representation of kinetics of the reaction, okay. So now if you see, if the option, let us see, 0 order, if it is a 0 order reaction, then y is equal to rate, okay, and x is equal to concentration. And if it is a first order reaction, y is equal to T half and x is equal to concentration. I think this option is only correct. So see, if it is a 0 order, y is rate and x is concentration. So we know that for 0th order reaction, R is equal to K into A to the power of 0, or I can say R is equal to K. So that means rate is independent of the concentration. Rate does not depend on the concentration, it is a constant value. So if this is your rate, y is rate and x is concentration, and it is a 0 order reaction, then rate is independent of concentration. The graph satisfies this equation. Now if you see for the second part, if it is a first order reaction, y is equal to T half and x is concentration. Now for first order reaction, we know that T half is equal to 0.693 by K, right? So what I can say, T half is a constant term, right? It does not depend on the concentration. So again, if I draw a graph between T half and concentration for first order, it will also a straight line because the concentration is not dependent here, or the T half is independent of the concentration, right? So that is why A is the correct answer here. Okay. Next, which of the following method is used as trial and error method to determine the order of the reaction? So this is your integrated rate law method is used as a trial and error method. Okay. Next, for a reaction A plus B gives C plus D, it is found that when the concentration of the reactant is taken as excess and the concentration of reactant A is increased by 4 times, the rate is increased by 2 times. The order of the reaction with respect to B is, okay. So it is found that when the concentration of the reactant B, okay, is taken as excess. So when you take the reactant 1 as excess, okay, that means it has no role in the rate law. Okay, so that is a zero order reaction with respect to B. So option number A is the correct answer here. Okay. Next, what is average rate and what is instantaneous rate? So now we will be doing 2 marker questions. Okay, so here is the definition. Average rate means it is at like along a certain span of time. Instantaneous rate means at that particular instant, right? So the rate of a reaction is measured over a long interval of time is called the average rate of a reaction. And the rate of a reaction measured at any instant of time or a very small interval of time is called as the instantaneous rate. Okay. Next, question number 2. What is rate law or rate expression? Define the rate constant or velocity constant or the specific reaction rate. So you know, for the rate constant how many words can be used. You should not get confused here. It can be rate constant, velocity constant or specific reaction rate. Okay, first let us talk about what is rate law. So rate law is the expression in which the reaction rate is given in terms of the molar concentration of the reactants with each term raised to some power which may or may not be the same as the stoichiometric coefficient of the reacting species in a balanced chemical reaction. Okay, so I can write, for example, I have a reaction like this, A plus B, okay, 2A plus B gives C. Now what is rate here? Rate law is equal to rate K into A to the power of X, B to the power of Y, right? Where X and Y is not equal to the stoichiometric coefficients. Clear? So rate law is the expression in which the reaction rate is given in terms of the molar concentration of the reactants with each term raised to some power which may or may not be same as the stoichiometric coefficient. Next, define the rate constant or velocity constant or specific reaction rate. So if you see what I can write, rate is equal to, or K is equal to rate by concentration of A and concentration of B, right? So I can say that rate constant is equal to rate if these concentrations are 1 molar, right? So that is the definition here. Rate constant of the reaction is equal to the rate. Rate constant is equal to the rate of a reaction when the molar concentration of each of the reactant is taken as unity. If you take this one 1, this one 1, then rate constant becomes rate, and that is the definition of rate constant. Okay. Next, what is zero order reaction? Give an example. This is very important question. I have given you 2 to 3 examples, so that is why the answer is looking big, but you have to remember any one of these examples. Okay. So the rate of the reaction is independent of the concentration of the reactant is called zero order reaction. Okay. The reaction in which the rate does not depend on the concentration at all, that is called as a zero order reaction. Example, first one is decomposition of ammonia to N2 and H2. Okay, this reaction. Second, decomposition of Hi to H2 and I2, and the third one is the combination of H2 and Cl2 to give you HCl. Okay, any one example you need to remember. Okay. Next, what is first order reaction? Give an example. Again, the rate of the reaction is proportional to the first power of the concentration of the reactant is called as first order reaction. You can see the general expression for rate law is like this. Okay, and if it is a first order, then it is equal to like this. So if rate is proportional to the first power of the reactant, rate is proportional to the first power of the reactant, then we call it as a first order reaction, right? So the rate of the reaction is proportional to the first power of the concentration of the reactant is called as the first order reaction. Here you can see rate is proportional to R to the power of 1, order will be equal to 1. Example, any one again here you can write radioactive decay order. Radium-226 decomposes to give you radon and helium, okay. Next you have decomposition of N2O5 and decomposition of H2O2. Any one example you have to remember from here, okay. Next, question number 5, define half-life period of a reaction or time for half change of a reaction. By how many times does the T half of zero order reaction increase if the initial concentration of the reactant is doubled? Okay, so half-life period is the time in which the reactant becomes half of its initial concentration, right? So you can see the time during which, or you can say this definition I feel more convenient. So the time taken to complete the reaction by 50% is called as half-life, and half-life is denoted by T half. You can write this definition, or you can write like this: the time during which the concentration of a reactant is reduced to half of its initial concentration. This is very important. Half of its initial concentration is called the half-life period of a reaction, okay. Now the next part, by how many times the half-life of a zero order reaction increase if the initial concentration of the reactant is doubled. So now if you know T half, okay, for zero order reaction is what? It is A naught, right, by 2K, okay. Now if I have doubled the initial concentration, T half will be equal to 2 times A naught by 2K, right? Means it has become double, the new T half dash. So I can write this as 2 times of T half, right? So the new T half is 2 times of the initial T half, right? So it increases by 2 times, clear? Increases by 2 times. Next, let us see the next question. What happens to half-life when a first order reaction, what happens to the half-life time of a first order reaction when temperature is increased? Give reason. Next, what happens to the half-life period for a first order reaction if the initial concentration of the reactants is increased? Okay, so if you first, before doing this question, the half-life for a first order reaction is what? 0.693 by K, okay. Now the first part, if you see, when temperature is increased, if temperature will increase, K will increase, right? K is directly proportional to temperature. So if K increases, T half will decrease, right? So the first one, it will decrease. Give reason, you have to explain this relation. Next one, what happens to the half-life period for a first order reaction if the initial concentration is increased? Now here you see there is no dependency of the half-life for the first order on the concentration of the reactants, right? In this equation, can you find any concentration of the reactant part? No, right? That means what? The half-life of first order reaction, this is the half-life of first order. The half-life of the first order reaction does not depend on the initial concentration, right? So that means even if you increase the concentration, you decrease the concentration, half-life value will remain constant, okay? So that is here no change, and here it will decrease, okay? So T half decreases. Why? Because as temperature increases, K is directly proportional, temperature increases, K increases, T half decreases, and for concentration, no change, okay. Next question, what is pseudo first order reaction? Give an example. You can see how important this question is. Very, very important question. Pseudo first order reaction. So this means what? Pseudo means false, okay. So a reaction was actually not a first order reaction, but due to some experimental conditions it becomes a first order reaction, then we call it as a pseudo first order reaction. Let us read the definition. Higher order reactions, okay, can be converted into first order by when one of the reactant is present in excess amount is regarded as a pseudo first order reaction. Higher order means generally we talk about the second order reactions. Second order reactions, if 2 reactants are there and one of the reactant is present in excess amount, okay, then that excess amount reactant is not considered in the rate law. because it is already present in excess. If you increase the concentration or if you decrease the concentration of that excess reactant, there is not going to be any effect on that, on the rate, right? So that is a dummy reactant present there. So that is why we can say that the reactant or the rate depends only on the reactant which is present in limited amount. So actually it was a second order reaction, but now it got converted to first order reaction because of one of the reactant present in excess. Okay, so you can see the example, acid hydrolysis of methyl acetate. Okay, any acid hydrolysis of esters, if you take, it is a first or pseudo first order reaction. So if you take here methyl acetate and water, right, water is present in excess amount and methyl acetate is present in limited amount. So even if you change the concentration of water, the rate is not going to be affected. So that is why it is a first order reaction. In this reaction, water is taken as large excess and hence the rate is independent on the concentration of the water. So the rate depends only on the molar concentration of methyl acetate, which is directly proportional to the first power of the concentration, hence it is a pseudo first order reaction. There is one more example, inversion of sucrose and or cane sugar. So here also water is taken in excess. These two examples are there in your NCERT, you have to remember both the examples. Okay. Next, question number 8, what is the effect of temperature on the rate of a reaction? Define the temperature coefficient of a reaction. Okay, so effect of temperature, you know, if the temperature increases, rate will increase. Okay, the rate of a reaction generally increases with the increase in temperature due to the increase in the number of activated molecules. Okay, now what is activated molecules? See, any reactant does not directly convert to product. Okay, you give some energy, it becomes first an activated molecule and then it gets converted to product. So if you increase the temperature, more number of molecules can go and form activated, they can activate themselves and then they can form the product, right? Next, what is temperature coefficient? This is important question. So temperature coefficient is the ratio of K T plus 10 divided by KT, means the rate constant at T plus 10 divided by the rate constant at T. Okay, and this value is all nearly equal to 2. Okay, 2 or 3. I'll add here, it is 2 or 3. Okay, now the temperature coefficient of a reaction is defined as the ratio of the rate constant of a reaction at a particular temperature to the rate constant at 10 degree lower temperature. Okay, so T plus 10 divided by 10 degree lower means T degree. Okay, next, how do you calculate the activation energy from the Arrhenius equation by graphical method? Okay, this is also important question here. So here first of all we should know what is Arrhenius equation. It is equal to K equal to A into e to the power of minus EA by RT. What are the different terms here? K is your rate constant. Okay, A is, we call it pre-exponential factor. Okay, then capital EA is activation energy. Okay, and T is temperature and R is gas constant. Okay, now if you take log on both sides, okay, first you will take ln, then we will get ln K is equal to ln A plus ln of e to the power of minus EA by RT, then power will come front, we will get minus EA by R. Then if you convert it into log, log K is equal to log A minus EA by 2.303 RT, right? Now if you take a graph for log K versus 1 by T, okay, then what you will get, the slope of the graph is this one, minus EA by, because you can see the graph is in this form. See, log K, okay, is equal to log A minus EA by 2.303 R 1 by T, right? So Y is equal to mx and C, right? So now if you see here, what I can get, slope is this m value which is EA by 2.303 R. Next, by calculating the slope from the graph, energy of activation can be calculated. Okay, so by calculating the slope of this graph, that is EA by 2.30 R, if you know the slope of the graph, then just by multiplying that you can calculate the activation energy. Okay, next, question number 10, explain the effect of catalyst on the rate of the reaction. So A catalyst increases the rate of the reaction by decreasing the activation energy and by providing a new path for the reaction. Okay, so what does a catalyst do? It lowers the activation energy and increases the rate of the reaction. So here you can see that if this is a reaction without a catalyst, okay, the solid line one, okay, so this was the activation energy required earlier. What is this? Is the activation energy required earlier. Now if you use a catalyst, the activation energy decreases and the reaction becomes faster. Okay, so how does catalyst affect? It affects the rate, or it increases the rate of the reaction by decreasing the activation energy. Okay. Next, what are the main criteria for the effective collision according to simple collision theory? So that means according to collision theory, when two molecules collide, okay, two conditions should be satisfied. The collision should have sufficient energy and should be in proper orientation. If these two things are happening, then that collision can lead to product formation. Okay, so that is activation energy and proper orientation of the molecules. Next, what is collision frequency? Give a drawback of simple collision theory. Okay, so what is collision frequency? The number of collisions per second per unit volume of a reaction mixture is called as collision frequency, and it is denoted by the word ZAB, right? Give a drawback of simple collision theory. So this theory considers the reactants as hard spheres and ignores their structural aspects. Okay, so according to collision theory, all the reactants are hard spheres. Okay, but that is actually not true, right? Reactants have their own specific structure, but it is assumed that all the reactants are spherical in nature. That is the demerit of this collision theory. Okay, now let us move towards the 3 marker questions. Okay, so name the factors affecting the rate of the reaction, or on which factors does the rate of a reaction depends. So the rate of a reaction depends on 3 important factors, like the nature of the reactant, temperature, concentration, catalyst, presence of light for photochemical reactions. But the main factors that you can write is temperature, concentration and catalyst. Okay, these are the main important 3 factors. Next, define molecularity of a reaction. What is an elementary reaction? Define order of a reaction. So molecularity is what? Number of species reacting, right? So the number of reactant molecules taking part in an elementary reaction which must collide simultaneously to bring about a chemical reaction is called as molecularity. Or simply you can write down the number of reactant molecules taking part in an elementary reaction is called molecularity of a reaction. Okay, the number of reacting molecules taking part in an elementary reaction. Okay, this much also if you write, that is also correct. Next, what is the elementary reaction? So if there is an example here, suppose NH4NO2 dissociates to give you N2 plus 2H2O, right? So how many reactants are there? There is only one reactant, so molecularity is 1, or we call this reaction as a unimolecular reaction. Okay. Next, what is an elementary reaction? The reactions taking place in one step are called as elementary reactions. Reactions taking place in one step. Define order of a reaction. So it is the sum of the power of the concentration terms of the reactants appeared in the experimentally determined rate equation for the reaction. Now for example, there is a reaction XA plus YB and rate is equal to K into A to the power of L and B to the power of M. So see here, L and X are different things. Okay, so X is the stoichiometric coefficient, L is the order with respect to A. So the order of the reaction will be L plus M. Okay, one second, yeah, L plus M, where L and M are determined experimentally. So order of the reaction is the sum of the power of the concentration terms in the rate expression. Okay. Next, question number 3, what is the slowest step in a complex reaction also called as? The slowest step in a complex reaction is called as the rate determining step. Okay, which step of a reaction mechanism decides the order of a reaction? The slowest step. Okay, for what type of reaction is molecularity and order the same? Okay, so the slowest step is called as the rate determining step. Then which step determines the rate of the reaction? Slowest step. For what type of reaction order and molecularity are same? So order and molecularity are same in the slowest step of a complex reactions. Okay. Next, difference between order and molecularity you can learn and write any three points you can remember. Okay, first you can see the definition. It is the sum of the powers of the concentration terms of the reactants in the experimentally determined equation. So by seeing the reaction you cannot say the order, right? But by seeing a reaction you can say its molecularity. It is the number of reacting species involved in the elementary or the simplest reaction. It is experimentally determined, it is theoretically calculated. It is derived from the rate equation, it is derived from the mechanism of the reaction. Order of the reaction can be 0, molecularity of a reaction cannot be 0 because there has to be any one molecule for the reaction to happen, right? Order of a reaction may be a fraction or whole number, molecularity of the reaction is always a whole number. Order of a reaction can change with the conditions such as pressure, temperature, concentration. Molecularity does not change for a chemical equation. Okay. Next, this is important, derive an expression for the integrated rate law for a zero order reaction, or derive an expression for the rate constant or velocity constant for a zero order reaction. Okay. So this derivation for zeroth order and first order are very important. So you should do it correctly. I will be showing you how to do it. So first you have to write in this way only. First, consider a zero order reaction, R gives you P. Next, zero order reaction is zero order reaction is which the rate is proportional to the zeroth power of the reactant, right? So according to the rate law, for zeroth order reaction you can write rate is equal to R to the power of 0. If you remove this proportionality, I can write rate is equal to K into R to the power of 0. Then if you remove this R to the power of 0 is 1, so I can write rate is equal to K, right? Next, what you can write, where K is the rate constant or velocity constant or for a zero order reaction. Now rate is also equal to minus dr by dt. See, if I use the differential equation law, what we know, rate is equal to minus dr by dt, right? And rate is also equal to K. So I can equate this equation and this equation and I'll get that minus dr by dt is equal to K, right? Next, rearranging the equation we get so now what I can do is I'll multiply this dt towards the right hand side. So what I'll get, dr is equal to minus K dt. Okay. Next, you can take integration on both the sides. So if you integrate it, my dr and K dt you will get. So derivation and integration will cancel each other, you will get R, and then here you will get dt integration will be T, and you will get one I which is an integration constant. Now you need to find the value of I. Okay. So to find value of I, consider T is equal to 0 and R is equal to R0, which R0 indicates the initial concentration of the reactant. So if I substitute this one, R became R0 is equal to K times T. T is 0 now plus I. So what I'll get, I is equal to R0. Now you have to substitute the value of I in the given equation, right? So what is I here? R0. So I'll get R is equal to minus KT plus R0. R0, I can just arrange this equation so that I'll get R0 minus R is equal to KT, or K is equal to R0 minus R by T. Okay, this is the equation that has to be remembered. Okay, same question for first order. Okay, okay, now we will do regarding the half-life. Okay, derive an expression of half-life period for a zeroth order reaction, or show that for a zeroth order reaction half-life period is directly proportional to the initial concentration of the reactants. Okay, so now you can see the first one. See, rate we already know, K value is R0 minus R by T. Now what is half-life definition? The time in which the concentration is half of the initial concentration, right? So if I say that K is rate constant, R0 is the initial concentration, R is the concentration at time T. Okay, then when T becomes T half, R will become R0 by 2, right? At T equal to T half, what should be the value of R? R0 by 2 means it will become half of the initial concentration, so R0 by 2. Then substitute these values here, right? We will get K is equal to R0 minus, here I will substitute R0 by 2 divided by T half. Okay, so now if I solve this, I will get 2 R0 minus R0 by 2 T half, and we will get R0 by 2 T half, and that is the equation. So if you just arrange it, T half is equal to R0 by 2K. Okay, so or we can say that T half is directly proportional to the initial concentration. Okay, Next, so this shows that T half is proportional to R naught for a 0th order reaction because 2K is constant. Okay. Next, you have to derive the integrated rate law for a first order reaction. Okay, very similar expressions we have to do. Let us see the derivation here. First, you can see that consider a first order reaction R is equal to P. Now, according to the rate law, rate is proportional to R to the power of 1. To remove this proportionality, we will multiply a constant. So, rate is equal to K into R to the power of 1. Next, if we write the differential rate law, rate is equal to minus dr by dt. So, if I equate this one and this one, I will get that minus dr by dt is equal to kr. Now, you can rearrange this equation, multiply dt on this side and r divide on this side. So, I will get minus dr by r is equal to k dt, right. Next, if you integrate the equation, you integrate this one and integrate this one, you will get 1 by r dr is equal to minus k dt, right. Now, 1 by r integration is ln r. Here it becomes minus kt plus this I is integrated constant. Now, again to find the value of I, you need to substitute t is equal to t half and r is equal to r naught, right. So, to find I, substitute t is equal to 0 and r is equal to r naught, where r naught is the initial concentration of the reaction R. So, you will get here ln r 0 minus k, this is 0 plus I, okay, where I is called the integration constant. So, you will get I is equal to ln r0 now. Now, you substitute this I here, okay. So, what I will get, if you substitute the value of I, you will get ln r is equal to minus kt plus ln r0, right. Then you will get kt is equal to ln r0 minus ln r, then you can divide, right. You will get like this, see, kt will be equal to ln of r0 minus, one second, okay, you will get here kt, okay, is equal to ln r0 minus ln r, right. Now, ln a minus ln b is equal to ln a by b, okay. So, this relation you should know that ln a minus ln b is equal to ln of a by b, okay. So, you will get this one, okay. Now, if you want to convert this ln to log, you will get kt is equal to 2.303 log r naught by r, okay. So, k, you can divide t here, k equal to 2.303 by t log r naught by r, okay. Next is your again half-life question. So, that for a first order reaction, the half-life period is independent of the initial concentration of the reactants, or derive an expression for the half-life of the first order reaction, okay. So, you can see here k value you can know, k equal to 2.303 by t log of r naught by r. Next, what you have to do, in the place of t substitute t half, and in the place of r you have to substitute r naught by 2, right. So, t is equal to t half, then r will be equal to r naught by 2, then just substitute these values, and once you substitute and solve this, you will get t half is equal to 0.693 by k, right. So, what will be the value you will be getting? T half is equal to 0.693 by k, right. So, you can see here that the half-life of the first order reaction does not depend on the initial concentration, right. So, that is why we can say that the half-life is independent of the initial concentration of the reactants. Next, derive the integrated rate equation for the first order gas phase reaction, okay. So, this is again an important question. So, let us do a question like this. You have suppose a reaction A, okay, gas phase. Let me write from this side. Okay. You have a reaction like this, A gives you B plus C, okay. Now, here at time equal to 0, initial pressure is Pi. At that time there were no B and C, the pressure was 0 and 0, okay. Now, at time equal to some T, okay, X amount of A has reacted. So, X amount of A has reacted. So, how much A will be left? Pi minus X amount of A is left. Now, if A is reacting, B will form 1 mole of A is giving you 1 mole of B. So, X amount of A will give you X amount of B, X amount of C. What is X here? X is amount of A reacted. Okay. Now what we can do? Now let us say that PT, it is what? Total pressure. PT is the total pressure at time t. Okay. So now if I add these all things, what I'll get? P total is equal to what? Pi minus x. Okay, this is the pressure of A, plus x plus x. So I will get what? Pi plus x. Okay. Now what is the value of x here? So PT value is known to you. What is the value of x here? 1 second. Yeah. What is the value of x here? X is PT minus Pi. Okay. Now what I can do? I can calculate all the values. Like I need the initial and the final concentration of A. So now I can calculate the final concentration of A, right? Not concentration, pressure, right? So I can calculate the final pressure of A. Okay. So final pressure of A is what? Pi minus x, right? And here I can substitute Pi minus, for x what I can substitute? PT minus Pi. Okay, right? Now if I solve this, I'll get Pi minus PT plus Pi, or I can write it as 2 Pi minus PT. Okay, so this is what? Final pressure of A, and this is the initial pressure of A, right? So now if I want to write the first order equation for the same reaction, right? A gives B plus C. Okay, at T is equal to 0, this is Pi, this is 0, this is 0. At T is equal to T, it is what? Pi minus x, this is x and this is x. Now once we have found out the value, so this is 2 Pi minus Pt. Okay, so now if I want to write the first order equation, so K is equal to, for first order we have 2.303 by T log of, right, initial pressure of A by final pressure of A, right? Now if you know 2.303 by T log of initial pressure of P is Pi, and what is the final pressure? Final pressure is 2 Pi minus P total. So that is 2 Pi minus P total. So this will be the expression of K for, this will be the expression of K for the first order reaction in the gaseous phase. Okay, so this derivation is like most likely to be asked because the questions are saturated for 0th order and first order, right? Some new questions, so this you should be very careful while reading the question and practice this derivation again and again. Next question, the temperature coefficient of the reaction is 2. How many times the rate of the reaction is increased when the temperature is increased from 300 to 350 Kelvin? So if you see 300 to 350, 5 times, like 10 times you are increasing 5 times, means it is like 300 to 310, then 320, then 330, then 340 and lastly 350, right? So it is 10 times, 10 times, 10 times, right? So 10 degree rise is there. Now for every 10 degree rise the rate increases by 2 times, right? So what will be the answer? 2 to the power of 5, that is 32 times. Okay. Next, so write the Arrhenius equation and state as what the symbols stand for. So you can write down here Arrhenius equation, K is equal to A into e to the power of minus EA by RT. K is rate constant, A is Arrhenius constant, E is the exponential, EA is energy of activation, R is gaseous constant and T is temperature in terms of Kelvin. Okay. Next, what is the energy of activation? Oxygen is available in air, yet fuels do not burn spontaneously at room temperature. Why? And what is threshold energy? So this is very important question, activation energy and threshold energy. So first let us see the answer here. So activation energy is the minimum excess energy acquired by the reactants upon collision to form a activated complex is called as the energy of activation and it is denoted by EA. Okay. So now let us understand this one. See, this is the reactant energies. Okay. And now this is the activated complex energy, means when the reactant reaches the activation energy, okay, and that time when the reactant reaches the activation, when the reactant becomes an activated complex and then it forms product. Okay, so the energy required here, the energy required here is called as the activation energy, right? So now this energy, see, a reactant cannot form product at any condition. At any condition, if you put a reactant, it will form product. It is not like that. The reactant must possess certain minimum amount of energy to get converted to product, right? So that minimum amount of energy that the reactant should have to get converted into product is called as the threshold energy. Okay, now initially the reactant was having this much energy. Now you need to provide certain extra energy to the reactant molecule to reach the threshold energy value, right? So that extra energy is called as your activation energy. Now let us understand with an example. Suppose there is a reactant having energy 5 joules. Okay, now for this reactant, for this reaction, the reactant must possess 10 joules of energy. Okay, or let me take it another number. Yeah, so now this reactant R should possess suppose 12 joules of energy to get converted to product, right? So this 12 joule will be what? Threshold energy, but reactant has an energy of 5 joule. Now how much energy is required here? 7 joules of energy is required, right? So how much extra energy you need to give to the reactant? 7 joules of energy, and that is called energy of activation. Okay, so you can see here the minimum energy that the reacting molecules should possess in order to form their products upon collision is called as the threshold energy. Okay, now what is the next question here? Oxygen is available in air, yet fuels do not burn spontaneously at room temperature. Why? So that is because, see, the activation energy that is required for the fuels to convert to activated complex is not available at room temperature. Okay, so the activation energy for combustion of reaction of fuels is very high at room temperature, therefore they do not burn themselves. Okay, next question 13, explain the Arrhenius theory of activated complex by using the potential energy level diagram. Okay, so here this is very simple question. So according to Arrhenius, what it says that the reaction can take place only when the reactant molecules collide to form an unstable activated complex. It exists for a very short period of time and then breaks to form the products. Okay, so Arrhenius equation or Arrhenius theory says that the reactants collide to form an activated complex, and that activated complex breaks down to give you the product. So you can see here reactants are there, they have collided to form an activated complex, and this activated complex breaks down to give you a product. Energy diagram or potential energy diagram you can see like this. This is the reactant, they have collided to give you an activated complex. This activated complex breaks down to give you the products. Okay, next, using energy distribution curves showing temperature dependence of the rate of the reaction, explain the effect of temperature on the rate of the reaction. Okay, very important question again this one. So now we all know that when temperature increases, the rate of the reaction increases, right? But why? What exactly happens when you increase the temperature so that the rate of the reaction is increasing? Okay, that is what you need to think here. So see, this diagram will make you understand the whole concept, but I want to give you a very simple example from your classroom which you can understand. Now see, in this diagram, okay, suppose this peak of the graph, okay, this peak of the graph tells you what? You can read the first line. The peak of the curve corresponds to the most probable kinetic energy, right? Most probable kinetic energy means the energy that is possessed by most of the molecules. Okay, now suppose for example you had a maths exam in your class, right? Maximum students, some students got very fail marks, some students got topper marks, but maximum students mark was between 60 to 70. Okay, so 60 to 70 range is what most probable marks of the students of this class, means the maximum number of students are falling in that particular range. Similarly, if you see, the maximum number of molecules have this energy EMP. Okay, this is the graph saying. Next, when the temperature is raised, the maxima of the curve moves to the higher energy side such that there is a greater proportion of molecules with much higher energies. So now what happens when the temperature is increased? So now let us imagine in the classroom. the maths sir found that many students are actually good, but they are scoring between 60 to 70. So he was not satisfied with that. So what your maths sir did, he tried to give you more push. Okay, he tried to give you more homework, he gave you more attention, he gave you more lectures, okay, he gave you more questions to solve, and he was giving you like day and night, he was following up with you whether you have done or not. So he pushed you more. Okay, so when you give more temperature, when you give more push, okay, next time when the exam happened, most of the students got 70 to 80 marks who were getting before 60 to 70 marks, right? So the most probable marks now became what, 70 to 80 because of the push of the teacher, right? Similarly, when you give more temperature, this was a temperature T, when you increase the temperature to T plus 10, okay, T plus 10, you can see the most probable. Now the particles are having this much energy. So the number of particles and the most probable energy of the particles increased from here to here. Now what is this? Now see, suppose the condition is like that, those students who will get 90 and above in the maths exam, they will get prize in the annual function, right? So earlier when the class average was between 60 to 70, there were 5 to 10 people who got above 90, right? Now when the teacher pushed more, the number of students getting 70 to 80 increased, and at the same time the number of students getting 90 above will also increase, right? So overall the performance will increase or not. So similarly, when the temperature was T, these were the particles which were having energy more than the threshold energy, means these were the particles which can be converted to products. But now after increasing the temperature, the number of particles which can form products increased to, from here this many more particles got added to that list, right? So when your teacher gave you more push, gave you more attention, now 20 students got 90 above, right? So that means what, the overall class performance will increase. The same thing is happening here. When you increase the temperature, the most probable kinetic energy increases, and also the students or also the molecules having energy greater than ET is also increasing. Okay, so now you can see earlier only these many particles were responsible for the rate of the reaction. Now these many particles are responsible for the rate of the reaction. Okay, so that is there. It is clear from the diagram that in the area A dash, B dash at T plus 10, showing the fraction of the molecules having energy equal or greater than the activation energy gets doubled, leading to the doubling the rate of the reaction. Okay, so that is why when you increase the temperature, the rate also increases. Why? Because the number of particles having energy greater than the threshold energy increases. Okay. Next is, what is the effect of the catalyst on the Gibbs energy of a reaction, and among the spontaneous and non-spontaneous reaction, which one is affected by catalyst? What is the effect of the catalyst on the equilibrium state and equilibrium constant in a reversible reaction? Okay, so now here if you see this one, effect of catalyst on delta G. So the formula of delta G is what? The formula of delta G is minus 2.303 RT log K. Okay, so now when equilibrium constant K is not affected by catalyst, so if K is not affected, delta G will also not be affected, right? So that is why in the first, the catalyst does not alter the Gibbs energy reaction. Among spontaneous and non-spontaneous, where it is affected? It is the spontaneous reaction which is affected by catalyst. Non-spontaneous reaction definitely needs some external support, okay, but spontaneous reaction happens by its own. So if you give catalyst, it will occur faster. Next, again, what is the effect of catalyst on the equilibrium state and equilibrium constant? No effect. Okay, so catalyst does not change the equilibrium constant and does not disturb the position of the equilibrium, but it helps to attain the equilibrium faster. Okay, fine. Now we will go towards the numerical questions. The first question here is, for a zeroth order reaction, the rate constant K is given, and what are the rates of production of N2 and H2? So if you have written, if you know, for the zeroth order reaction, R is equal to K into NH3 to the power of 0, right? So that is equal to K, and the K value is 2.2 into 10 to the power of 4. Okay. Now coming to this one, I can write that R is equal to K is equal to 2 into 10 to the power of 4. Now what are the rates of production of N2 and H2? So if I know this rate law, rate is equal to minus 1 by 2 dNH3 by dt, okay, is equal to dN2 by dt, okay, is equal to 1 by 3 of dH2 by dt. Okay, so now if I solve this, what is the value of rates of production of N2 and H2, right? So if I see dN2 by dt, okay, that is equal to rate, and rate is equal to 2 into 10 to the power of 4. Okay, next if I see dH2 by dt, okay, dH2 by dt will be what? 3 times of rate, right? So I can write 3 into 2 into 10 to the power of 4, so that is equal to 6 into 10 to the power of 4. Okay, so answer here will be 2 into 10 to the power of 4 and 6 into 10 to the power of 4. Okay, not minus 4, it is plus 4. Okay, next question number 2. Question is given here, H2, express the rate in terms of changes of H2O2 and H2O with time. So that we can do. So we know rate will be equal to, right, minus 1 by 2 of dH2 by dt, okay, is equal to minus dO2 by dt, okay, is equal to plus 1 by 2 of dH2O by dt. Okay. Next, when O2 is decreasing at 0.23 mole liter inverse second inverse, what is the rate of H2O increasing? Okay, O2 and H2O it is asked, right? So let us write the relation between O2 and H2O. So it is minus dO2 by dt, okay, is equal to 1 by 2 of dH2O by dt. Right, now we need the O2 value is given to you, you need to find dH2O by dt, right? So I can write dH2O by dt is equal to 2 times of dO2 by dt. Okay, so I can substitute 2 times of dO2 by dt is 0.23, okay, so that is 0.46. Clear? So you can find this answer, that is 0.46. Okay, okay. Next, question number 3. In a chemical reaction, A plus B gives you C plus D. The concentration of reactant A alone is increased by 2 times, the rate increases by 4 times, right? So if you are increasing A 2 times, rate increases by 4 times. That means with respect to A, it is second order, right? So let me write like the rate is equal to K into A to the power of X and B to the power of Y. And we know now from the statement that X is equal to 2. Now, if the concentration of both A and B are increased by 2 times, okay, the rate increases by 8 times. Now see, if you have increased the rate, if you have increased the concentration of by A by 2 times, rate will increase by 4 times. If you have also, so that in that 8, I can write it in the form of 4 into 2, right? Now this 4 has come, why? Because you have increased the concentration of A. Now, if you are doubling the concentration of B, then rate also becomes double. That means it is because of what? I can say Y is equal to 1. If you double the concentration of B, rate also becomes twice, right? So, total the effect comes out, the rate has become 8 times. So, what is the order with respect to A? With order with respect to A is 2, with respect to B it is 1. Okay. Next question, this is important question. Okay. So, following data has been obtained and you need to calculate the first question is the order with respect to A and B. Okay, so see, so let us see that let the rate law, okay, I'll write here, see, let the rate law for the reaction is A to the power of X and B to the power of Y. Okay, now first objective is to find X. Okay, so if you want to find X, that means you have to find 2 reactions where B is constant. Okay, so which are the 2 reactions where B is constant? Reaction 1 and reaction 3. So 0.2, 0.3, 0.4, 0.3. Okay, so reaction 1 and reaction 3. So I will write R1 is equal to 2 into 10 to the power of minus 3 is equal to K into A value is 0.2 to the power of X, B value is 0.3 to the power of Y. And R3 value is 2 into 10 to the power of minus 3, K into 0.2 to the power of X, right? And sorry, this is I think wrong, I have taken wrong value, this is 4, we'll check it, but as far as I remember, this is 4, okay, and this is 0.3 to the power of y. Let us check once again. R1 is 2, 0.2, 0.3, 0.4, 0.34, right? So 0.4, 0.34, yes. Now what I'll do, I'll divide R3 by R1. So if I divide this one, I'll get 4 into 10 to the power of minus 3 divided by 2 into 10 to the power of minus 3 is equal to k into 0.4 to the power of x, 0.3 to the power of y divided by k into 0.2 to the power of x and 0.3 to the power of y. Okay. So now if we solve this, we'll get 2 is equal to R3 by R1, and we will get here 2x, right? So if I now solve this, I'll get x is equal to 1. Okay. So I got x value is 1. Now the next task is to find y. Okay. Now to find y, what you should do, you should select such reactions where A is constant. So in where reactions A is constant, in 1 and 2, right? So you can write R1 values already we have. R1 is 2 into 10 to the power of minus 3 is equal to k into 0.2 to the power of x and 0.3 to the power of y, and you have R2 value is 2 into 10 to the power of minus 3 k into 0.2 to the power of x and 0.1 to the power of y. So you can see here 0.2, 0.12. Now what we can do, we can divide R1 by R2. So that is 2 into 10 to the power of minus 3 divided by 2 into 10 to the power of minus 3 is equal to k into 0.2 to the power of x, 0.3 to the power of y whole divided by k into 0.2 to the power of x and 0.1 to the power of y. Right. So now if you cancel these all things, we'll get 1 is equal to 3 to the power of y. This one I can write 3 to the power of 0 is equal to 3 to the power of y, or I can write 0 is equal to y. Okay. So x is equal to 1 and y is equal to 0. So what will be the first question? What is the order? With respect to A, it is 1, and with respect to B, it is 0. What is the rate law? So if I want to write the rate law now, it is k into A to the power of 1 and B to the power of 0, or I can write like this, k into A to the power of A, right? This is the second question. Now third question, what we have to find, what is the rate constant? So rate constant is equal to what? R by A naught, A concentration. So you can put 2 into 10 to the power of minus 3. I am taking the first experiment data. A value is 0.2, right? So it will get 10 to the power of minus 2. Next, fourth one. What is the half-life? So since it is a first order reaction, so first order reaction T half is 0.693 by k, or I can substitute 0.693 by 10 to the power of minus 2, and that is 69.3, okay, seconds. Clear? Okay, next question number 5. A reaction is first order in x and second order in y. Okay, so let us write down the rate law. A reaction is first order in x and second order in y. Okay. Next, write the differential rate law. Okay, this is already done. Second question, how is the rate affected on increasing the concentration of y 3 times? Okay, so let us see now. R dash is what? K into x into concentration of y is increased by 3 times. So what I'll get? This will become 9 k into x into 3y. Okay, so I'll just remove this 3 here. Okay, so now I'll get 9. What is this? K x y square, this is r. So I have r dash is equal to 9r. So that means the rate increases by 9 times. Next, third point, what is the SI unit of the rate constant? Now see, rate constant will be what? I can write r into x and y square, right? So if I just substitute, rate unit is always mole, liter inverse, second inverse, okay, and concentration unit is mole, liter inverse, and here it is mole, liter inverse square. So now if I substitute this one, it is mole, liter inverse, second inverse, then you have mole, here mole cube I'll get, right, mole cube I'll get, and liter I will get minus 3. Okay, Now if I solve this one, I will get mole 1 minus 3, it is minus 2, then liter I will get minus 1, this will become plus 3 liter square second inverse. Okay, clear? Next, question number 6. In a zero order reaction, the time taken to reduce the concentration of the reactant from 100 to 50% is 40 minutes. That means for zeroth order reaction, T half is 40 minutes. Okay. Next, what is the time required to reduce the concentration of the reactant from 25% to 12.5%? Okay. So now see, if this question would have been from the first order reaction, okay, then whatever time it takes, 100 to 50, it is also half, 25 to 12.5 is also half, right? It would have taken the same amount of time. But because it is a zeroth order reaction, the value will change. Okay. So what is the zeroth order reaction for half-life for zeroth order formula? A naught by 2K, right? So what's the value of K here? I can substitute A naught by 2 into T half, right? So that is A naught is 100, means for this one 100 to 50, right? 100 and 2 is 40. So I get 100 by 80, or I can say 10 by 8 minute inverse. Okay. Now next T half, the new T half will be what? Again A naught by 2K, right? So that is given, A naught value is 25, okay. 2 into K value is 10 by 8. So I'll get 10 into 8. So if I solve this, I'll get 5 2s are 5 5s are 2 4s are and 2 2s are. So you will get 10 minutes. Okay. So from 25 to 12.5 it will take 10 minutes, whereas from 100 to 50 it took 40 minutes. Okay. So if it is a zeroth order reaction, it always depends on the initial concentration. Okay, next question number 7. The time required to decompose SO2Cl2 to half of its initial concentration is 60 minutes. If the decomposition is a first order reaction, calculate the rate constant of the reaction in seconds. Okay, this is very simple question. So you have been given with T half, that is 60 minutes, right? Next, do you know this formula? K is equal to, for first order, 0.693 by T half. Okay. Now you have to calculate it in seconds. So that is 0.693 by 60 minutes into 60 seconds. To convert it into seconds, we have to multiply this one. So if we solve this, you will be getting 1.925 into 10 to the power of minus 4 second inverse. Okay. Check this calculation once again. Next, question number 8. Calculate the time in seconds for the decomposition of nitrogen pentoxide which follows first order kinetics when concentration of N2O5 is dropped from 0.1 to 0.01. K value is given to you. Okay, so we have this, let us note down the values here. So the order is first order, okay, it is a first order reaction. Then concentration changes from 0.1 to 0.01. So A naught value is 0.1 and A value is 0.01. Okay. Next I have K value is 6.22 into 10 to the power of minus 4 second inverse. Okay. So what I have to calculate here? Time I have to calculate, right? So for first order we know T is equal to 2.303 by K log of A naught by A. Okay. So it is 2.303 by K is 6.22 into 10 to the power of minus 4 log of A naught value is 10 to the power of minus 1, 10 to the power of minus 2. So now this minus 2 goes up, it becomes plus 2 minus 1 is log 10. So we will get the same value. So if I solve this, 2.303 by 6.22, okay, into 10 to the power of 4 I will get, right? So the answer, if you solve this, you will be getting 3.7 into 10 to the power of 3. Okay, you can check the calculation. Next, question number 9. For a first order reaction, show that the time required for 99% completion is twice the time required for completion of 90%, or you have to show this one. Okay. So here how you should do, you should solve LHS and RHS separately, and then you have to show that LHS is equal to RHS and hence proved, like how you do in maths, right? So let us do first T 99%. Okay. So if you remember first order reaction, T 99 will be T is equal to 2.303 by K log of A naught by A, right? This is the formula. Now for T 99%, what I can substitute? 2.303 by K log of 100 by 1, right? Now see, 99% means what? 99% completed, 1% will be remaining. This is log 10 to the power of 2. It will come 2 log 10. So I will get 2 into 2.303 by K. Okay. Now this is what? In LHS. Now if you want to calculate RHS, it is what? T 90% you want to calculate, right? That is equal to 2.303 by K log of 100 by 10, right? Now if I solve this one, this will become log 10, that is 1. So 2.303 by K. Now 2 times of T 90% will be equal to what? 2 into 2.303 by K, right? So now you see RHS and LHS is same, right? So that is why hence proved. Next question number 10. T half of a reaction is 10 minutes for the first order kinetics. What percentage of the reactant remains unreacted after 50 minutes? Okay. So let us start from like this 100. In the first, the half-life is 10 minutes, right? In the first 10 minutes it will become 50. In the second 10 minutes it will become 25. In the next 10 minutes it will become 12.5, right? In the next 10 minutes it will become 6.25, and in the next 10 minutes it will become 3.125. Okay. So how much percent will be left unreacted? 3.125. Okay. Now this we are able to apply because it is a first order reaction. In first order reaction, the half-life never changes, whatever will be the initial concentration. But in zeroth order, the half-life depends on the initial concentration. So this half-life and this half-life will not be same. Okay. Next, question number 11. A first order reaction takes 40 minutes for 30% decomposition. Calculate the T half. Okay. So this is also a simple question. It takes time given is 40 minutes, right? For 30% completion, whenever percentage is given, take the initial concentration as 100. Now 30% has completed, that means how much is remaining? 70. Okay. 30% decomposition. Okay. So now if I have this one, K is equal to 2.303 by T log of A naught by A. Okay. So how much will I get this one? So we have to calculate this value. Okay. So let it keep it like this. This is the value of K. Okay. So one second. Next you have to also calculate the half-life. So T half formula is what? 0.693 divided by K. So you can substitute 0.693. K value is what? 2.303 log of 10 by 7, right? This will be 10 by 7 into 40. Okay. So now if I see this, you can see the answers here. You will get, this one is 8.918, okay, into 10 to the power of minus 3. And once you substitute this one, so I think this substitution may not be visible here. Let me write it again. Okay. So now it will be 0.693 by K value is 8.918 into 10 to the power of minus 3. If you solve this, you will get 77.7 minutes. Okay. Next question number 12. The graph of log K versus 1 by T for a reaction is linear with intercept of 10 and slope of this one. Calculate the frequency factor and EA of the reaction. Okay. So if you have learned the Arrhenius equation, the formula is like this: log K is equal to log A minus EA by 2.303 R into 1 by T. Okay. So now we have this one. Okay. This is log K. We have the equation like this: y is equal to mxc. Okay. So what is the value of x? It is 1 by t. Okay. Slope is minus EA by 2.303 R. Okay. And this one is log A. Okay. Y intercept is log A. Now question is saying that the y intercept is 10. That means I can say that log A is equal to 10. Right. then what is the value of A? A is 10 to the power of 10, right? We'll take antilog on both sides. Then calculate the frequency factor, already done, and EA of the reaction. Okay, so EA value, the question is saying that the slope is this much, right? So I can say slope here is this much, so slope minus EA by 2.303 R is the slope, and according to question this is equal to minus 5.1 into 10 to the power of 3, right? Now what is the value of EA then? It is equal to minus minus we can cancel, we will get 5.1 into 10 to the power of 3 into 2.303 into 8.314. Okay, now if you solve this you will be getting EA is 97.65 and A is 10 to the power of 10. Okay, clear this one. Next, question number 13. The rate constants of a reaction at 500 and 700 Kelvin are given to you. Calculate the activation energy. So this is simple formula. When two temperatures are given, we have one formula like this: log K2 by K1 is equal to EA by 2.303 R T2 minus T1 by T1 into T2, right? So what are the values given to you? T1 is 500 Kelvin, T2 is 700 Kelvin, right? And you have here K2 value is 0.07 and K1 value is 0.02. Okay, you have to calculate the EA value. So that is log of 0.07 by 0.02 is equal to EA by 2.303 into 8.314. Okay, so T2 is 700 minus 500 divided by 700 into 500. Okay, so now if you solve this, we will get EA value as 18.228 kilojoule. Okay, EA as 18.228 kilojoules. Okay, so clear. Now let us see the next question. The first order rate constant for the decomposition of ethyl iodide at 600 Kelvin is given to you. Okay, so that means T1 600 Kelvin and rate constant is 1.6 into 10 to the power of minus 5. Its energy of activation is given to you. Okay, EA value is how much? 209 kilojoule. Here you should be always be careful. The activation energy should be in the terms of joules. Okay. Next, calculate the rate constant at a temperature of 700 Kelvin. Okay. So first let us write the equation. Log K2 by K1 is equal to EA by 2.303 R. Okay. T2 minus T1, right? So 7. Okay, let me first write the formula. T2 minus T1 by T1 into T2. Okay, so if I substitute this one, this is log of 0.07 by 0.02, right? Oh, sorry, this is not the value. Okay, log K1 is 1.6 into 10 to the power of minus 5, right, into K2. EA is, here you should convert it into kilojoules, okay, joules, 2.303 into 8.314. Next, T2 is how much? 700 and 600. So 700 minus 600 divided by 700 into 600. Okay, so now if you solve this value, you can see the calculation here. Okay, so once you put all these values, you will be getting the answer as 6.35 into 10 to the power of minus 3. So you can check the calculation and tell me whether you are getting the same answer or not. Okay. Last question here. The first order rate constant for the decomposition of N2O5 at 0 degrees Celsius, okay, 273 Kelvin, is how much? 5.2 into 10 to the power of minus 4 minute inverse. If the energy of activation is 6200 joules, calculate the temperature at which the rate constant, is 6.358 into 10 to the power of minus 6 minute inverse. Okay. So you have to calculate the temperature at which the rate constant has become 6.358 into 10 to the power of minus 6. Okay. So let us do this. You will have log of, right, K2 by K1. So we will have K2 value is 6.358 into 10 to the power of minus 6, okay, divided by, okay, first thing we need to solve is we need to substitute. Before first we need to write the formula, right? So I think all of you have remembered the formula by now. This is the third time I am writing in this equation. So 2.303, then you have T2 minus T1 into T1 into T2, right? So now if I see log of K2 is 6.358 into 10 to the power of minus 6, okay, whole divided by K1 is 5.2 into 10 to the power of minus 4, okay, is equal to EA by 2.303 or 8.314, okay. Now here if I want to write EA is 6200, right? So we can substitute that also. EA is 6200, T2 minus T1. So T2 I have to calculate, right? T1 is 273 into 273 into T2. Okay, so now you have to solve this all and find the value of temperature. So if you solve this and you find the value of T will be 294.69 Kelvin. Okay, so you can substitute all these values and check the answer and let me know if you are getting the correct answer or not. Okay. Now coming to the important topics in this chapter. First you need to focus on the rate law, how to write the rate law and all. Second, you should know how to calculate the order. We did a question like the long question where table will be given, from that how to predict the order. Then you should know integrated rate law and half-life equation, and also you should know the examples of zeroth order and first order reactions. Then order and molecularity, difference between, and you should know first order example, molecularity some example you should know. Effect of temperature, here you should know the Arrhenius equation, right? Arrhenius equation plus the graph. You can see question from graph also we did. And next, collision theory is you should know its postulates. Okay, so these are the important topics that you need to cover from this particular chapter. Okay. Fine. So students, once again here I want to remind you about the PU2 success blueprint test series. So I have already given you all the details. So if you want to if you are interested to buy it, please go to the description section. There you will find the link for this. Click on that link and then you will be directed to the website, and there you can purchase the test series at a discounted price of 599 rupees. Okay. So if you really want to ace your preparation, do not delay, just go and buy the test series as soon as possible. Okay. So thank you students now, and I hope you would have completed. I know this lecture would be little lengthy, but yes, trust me, if you watch this one video and do all the questions, remember all the questions and do writing practice, then this one video is enough for chemical kinetics. I can assure you that no questions from outside of these content will be asked in the exam. So that is why give your time and do your best, all the very best for your preparation, and thank you for watching. Do not forget to subscribe the channel if you like this video.